but still make it safe.
All right. So let's come back to our main lecture. So in the next few weeks, we will talk about storage device. And before that, let's have a quick add-on. So last time we say there is a bonus, like 6 points, and this is how it goes. You can ask any questions on the chat box, or if you want to ask a question in a post to raise your hand, we are also welcome. So you need to include like what's your name, student ID, the date you ask the question, and then what is your question. And if you are using the WebEx, then please do a screenshot that there is no actually you have this question. And then you can send the question to the email. Okay. But our TAs will not respond to your email very reactive because there's too many emails. So we will do the accumulations and then we will announce it at the very end of the semester. Okay. So this is about the extra points part. Okay. So let's do a fast recap. Sorry, I think this one. Okay. So last time, I think the key thing is we're going to let you know actually for AI and ML applications, actually their model size or actually the memory required by the applications actually grows very fast and it is faster than the memory capacity. So like in the past 10 years, actually the memory requirement or actually the model size increased like 10 to the 7 times larger than at the very beginning, like CL model in 2012. But on the other hand, the memory capacity grows in a very slow path. Like it just doubled in 2 years. You can see in the figure for A100 in 2020, actually, the memory capacity is 40 gigabyte. And when it comes to like X100, like published on 2022, and it's only 80 gigabytes. So this is only a double. So this memory capacity increasement trend cannot catch up with this memory requirement for the AI ML. And because this trend, so most of the research, they are thinking about how to, for example, how to do the quantization things to quantize the data point to like to quantize for the integer, maybe to like 2-bit or even like 4-bit, those kind of things. Okay. But on the other hand, like because quantization sometimes it will lose your accuracy, you will hurt your accuracy. So if you don't want to hurt your accuracy, a possible solution is to move your data from GPU to the CPU's memory, let's say DRAM. And if this is also not sufficient to capture all the data set, then you can move it, or the model, you can move it to the storage. So this course is going to let you know actually there's different kind of device and what is the like hardware-based operations for those kind of hardware. Okay, so this is our agenda for the following few weeks. We'll first talk about the concepts of storage device, and then we'll first talk about the hard disk drive part. I think for most of the hard disk drive part, it is quite overlapping with the things you learned in the operating systems. For example, how it works, like it is a hard HDD, so there is a read head, there is a write head, and then how to read out data, how to write data. And because because the write head is larger than the read head, so there is a things called single magnetic recording drive, SMR, and this is super practical because in current market you can find this kind of SMR drive. It can offer you like 1.5 or even double the capacity larger than hard disk drive. So you can, if you see something like 15 terabyte or like 20 terabyte, usually this is because you're using the SMR. So there's a little bit different compared with the operating system. Is we will talk more about the RAID. So if you have multiple hard disk drive, for example, you have 6 or you have 10 hard disk drive, then how to gather those kind of hard disk drive together to make sure reliability or to measure the performance. So this is about the rate. After that, we will talk about the solid state drives. So in the operating system, actually, we only talk about the reprogram and erase part, right? And we talk about a little bit about the like MLC part. So this time we'll recall it again in a very similar way. And this time we will add several more advanced research oriented topics. For example, if there are retention errors, then how to handle retention errors. And then we will have more, we'll take a deep dive into the flash translation layer. So we'll talk about how to run or like how to deal with those kind of address remapping, how to deal with the lifetime issue, how to let your SSD to work healthier and then to have better performance. So before all the things, we know we need to have a big picture about our computer architecture. Like the very fundamental question is why there is memory hierarchy. So I think this is a short answer. It is about to balance access time and cost, or you can say it is about the price in most way. So there are three main layers. The top layer will be the CPU cache. So CPU cache TLB, they are using the things called SRAM. So SRAM is kind of a memory device. So this kind of memory device, it offers a super short latency. Usually SRAM is like 10 times faster than DRAM. Okay. But also the price for SRAM is more expensive than DRAM. It is pricey, and also SRAM requires larger space. I mean the manufacturing side. So actually, usually if you look at your CPU cache, usually your size for SRAM, there's only like megabyte level. Okay. So you really, or maybe there's no SRAM, you can offer you like 1 gigabyte. I think there's no. So DRAM, on the other hand, it is a little bit slower. You can look at the latency, it is about 10 to the 100 nanoseconds. So for DRAM, actually, the price is cheaper than SRAM. The reason is because the manufacturing part. So actually, for DRAM, it is possible to offer you like 16 gigabyte or like 32 or even very few. There are 64 gigabyte, those kind of larger memory capacity. Okay. So there is another thing in your computer as non-volatile device. Usually we call them storage device, hard disk drive and SSD. So hard disk drive and SSD, actually, if you look at the latency, the gap will be more than 3 orders, like 1,000 times slower than memory. Okay, I think there is one question as if CPU cache is super fast and memory device are like way slower, then if now I have a lot of budget, why not just build a systems with only like cache and memory, right? Just like I'm very rich, so if it is possible to build a system with only cache and memory, and we just remove the storage because storage is so slow, and the quick answer is no, because for the system level, it is not only performance, because for the CPU cache and memory, actually there are not non-volatile, which means if you power off your systems, if there is a power shock, something like that, then your data in both devices will get lost. Okay, so if you want to make sure your data is 100% safe in any situations, like you need a non-volatile device. And currently, the mature solutions for non-volatile device, there are only storage device. I mean, there are a lot of research works. There are also a lot of like Samsung or SK Hynix. They're saying they are going to launch a very new non-volatile memory, but there's still no productions they can do. They can have non-volatile capability in the memory level. I mean, there are some in the research, but not in the production. I mean, you cannot buy it now. Okay, so storage, there is still the value here. The value is to keep your data non-volatile, to keep your data will not get lost no matter what kind of situation happens. Okay. There is another aspect is like why memory hierarchy matters. Like if something like if you have good amount of the budget, maybe you need storage, then why we need the memory? Okay, so the thing is because most of your applications or most of our programming code, they shows locality. So I think you know locality, there is a like spatial locality, there are temporal locality, and spatial locality means like when you are going to access the data, for example, when you are writing your code, maybe you declare an array, and when you are going to access the array, maybe you access in a very regular pattern. For example, you will always access the next array sort. So then this is called a spatial locality. And temporal locality is just like you will access the same data in the near future. So because of those kind of locality, so CPU cache doesn't need to be super large. Like there's only like a few data will be reused in the short term. So actually, if you are using Intel CPU, there is, I think several years ago, there is a report that's going to let you know your CPU cache hit can be up to like more than 90%, and for some cases, they can be 99%. So which means there's only 1% of the data will go to the main memory. So if there's like 99% of data that can be cached in the CPU cache, then even you are going to enlarge, you are going to equip with larger CPU cache. It cannot help that much. I mean, you pay more money, but you don't really get a same amount of the performance improvement because smaller CPU cache can already absorb 99% of the assets. Okay, so if you are going to double your cache, then probably you can make the 99% maybe to 99.5 or 99.9%, but you need double of the budget. Okay, so this is also another perspective of why memory hierarchy matters. Okay, I think there is another interesting thing. I'm not quite sure in this course if we have time to talk about this point, but if there is time, I will talk about this point. So let me just make them a little bit ahead to talk about it now. So you already learned operating systems. I mean, even you did not have the master version, you have in your bachelor, right? You have in your undergraduate. So for the operating system, actually you learn a lot about, there is scheduler, there is memory manager, there is something like patch flow. Patch flow, there's context switch, all those kind of stuff, right? So actually those kind of stuff, they are all, you can think about they are all function. So in the kernel code, they are all function one by one. There is a scheduler code, there is a memory management code, they are all code. So which means when CPU is going to run those kind of code, it needs to take time. Okay, so but how long it takes, it depends on how complex your code is. If you write a scheduler, it is super complex, then when it is going to compile into like machine code, then you need more time to run your complex scheduler. So usually in the current Linux, when you are going to run any OS service, usually it is between like 100 nanoseconds to 10 microseconds. Okay, so 100 nanoseconds, like what is the feeling of 100 nanoseconds? Usually when you buy a CPU now, if you say it is a 3 gigahertz or like there is a 5 gigahertz CPU, so which means your CPU can finish one instruction usually in like 0.3 to like 0.2 nanoseconds. So 100 nanoseconds, you can think about like you can finish like around like 500 of the machine code. Okay, so 500 of machine code, if you translate back to a C code, usually like you can finish like 100 of the C code line. And the reason is because when you are going to compile your C code to the machine code, there's a lot of extra intermediate code there. So it is not really one-to-one. Like usually one line of code of C you usually need like 5 to 10 machine code to finish it. Okay, so 100 nanoseconds, you can think about, usually it is about 100 line of C code. So to run 100 line of C code, it doesn't really matter because when you are going to run a C code, it is in a CPU, right? But the thing is, if you are going to run some like heavier or like some more complex functions, such as context switch, usually you will need 10 microseconds, 1 to 10 microseconds, because the line of code, there is more line of code there. Okay, and 10 microseconds it still doesn't matter because 10 microseconds is still way faster than storage device, right? But the thing is, 10 microseconds actually it is already like a store length to access the data in memory. Okay, so what I'm going to say is, if there is a storage device, like the exit latency is very close to operating system running time. For example, now there is ultra low latency storage device. Like there are proposed by Intel and Samsung, and their response times is around like 1 to 10 microseconds. So in this case, so we always do context switch, or actually we just let the CPU to access the storage. So this will be a new research issues here. Okay. In the past, people doesn't really care at this point. Actually, operating system it really evolves, but the time doesn't change that much. The things really change is the storage device, because in the past, the response times of storage device it is around like 100 microseconds to 1 millisecond. But in recent like 5 years, because the manufacturing technology becomes so advanced, like TSMC, they try to use like 3 nm or like 2 nanometers, those kind of new technology. So you can have faster latency here. So if one day, like those kind of device become so general, I mean, those kind of super short latency device becomes so general, then we need to think about what kind of operating systems should we design. Okay, so coming back to our this like current situation, if now our storage device is 50 microseconds, 1 millisecond, actually it is still quite slower than operating system. So there are two very important operations. One is to get data from memory. So this is memory, right? You do the array allocations, or like you do linked list. You allocate a linked list, which means you need a heap, those kind of things. Then when the data is in the memory, then usually CPU will use the load and store instructions to directly access data in the memory. Okay. So when CPU is going to access those kind of data, usually there is no operating system involved, because operating system takes more time, right? And memory now is faster. Okay. But on the other hand, if we are going to get the data from a storage device, which means, for example, you have a movie and the movie is in the storage device, when we are going to get them, usually what we are going to use is things called system code. So system code and page for handler, those kind of stuff, they are all part of the operating systems. And the reason when the CPU use different manner to access the data in memory or storage is because storage is so slow. So if CPU directly use a load store instruction to get the data from storage device, then CPU should busy waiting here for a super long time. Because like this is 1 nanosecond and this is like 50 microseconds. So now CPU needs to wait for like 50 microseconds, which means it is around 50,000 more times. More CPU cycles will be wasted here. Okay, so a better way is to use some software solution to hide this long latency. And this is what you learn. Like we need to run the context switch to switch to other process, so other process can do their own procedure. And the prior one, they need to wait for the data to be moved from storage to memory by using like DMA, those kind of stuff. Okay. So getting data from storage, because storage is so slow, so there is a chance to use the operating system to hide those kind of storage hardware latency. But because memory is so fast, so if now you are going to use the operating systems, you are going to call the operating system to do some optimizations when the CPU is going to access the memory, then actually the overall time will become longer because CPU needs like 100 nanoseconds to run operating system, but memory, we only need 10 nanoseconds to do a response. Okay, but maybe you have a question will be like, so, but what you may learn will be there is a memory manager in the operating system, right? So what are those kind of design for? So usually those kind of designs, they are for allocation. So now if you are going to allocate a huge memory for like one process, then because we need some management part, so we cannot directly just access memory and that's finished. We need to do some more complex. We need to do some more complex management. So there is a need for operating systems. Okay. So for that case, then CPU needs to run operating system to access the data from the main memory. Okay. Okay. So this is like a very important concept for current computer architecture. Okay. So after talking about the architecture part, let's move to a more higher level stuff. What is storage and what is data? Because we say the data is stored in the storage device, right? So what is data? So data, as you learned, this is a sequence of 0 and 1 because we are using the binary systems, right? But have you ever thought about then how those kind of storage devices store 0 and 1? Because 0 and 1 is a more abstract, right? This is a kind of concept. So what is really the storage device to store these kind of things or to represent those kind of stuff? So the thing is, like in the device, actually there is a material. So this kind of material can switch between two states, like 0 and 1. And this kind of material is just like you learn your chemistry course. So that kind of material. So sometimes for some device, we'll use like chemistry stuff to represent 0 and 1. And sometimes we'll use some physics stuff. For example, there is a magnet. So there is like current, the electricity part. Okay, so it depends on different device. For example, for hard disk drive, actually it depends on the magnetic field. So this is the like ferromagnetic field or anti-ferro, then it means like the data is represented by like 0 or 1. Okay. And for SSD, actually it is about the voltage level. Is this a high voltage level or a low voltage level? So it can represent data 0 and 1. So actually there is no, it doesn't really to store this kind of digital stuff in your device, because for device part, they're all analog. Okay, so what we store in the device, they're all analog stuff. So DRAM actually it is about the capacitor. So the capacitor is charged or not. It let the DRAM can show it as a 0 state or 1 state. And there is also new emerging device like ReRAM, PCM, and STT-RAM. They are using the resistance to show about the data. Okay, so there is another characteristic we already told so much before this slide is non-volatility. So non-volatility is it possible to keep the data even when the power of the device is off? Just like you think about even if there's no power. And DRAM is volatile. So data stored in DRAM will get lost if there is no extra power supply. Okay, so there is another like people like to talk about as granularity. So granularity is about the minimum read-write size of each device. So when we are saying, hey, actually there is a byte-addressable stuff, usually like DRAM, IRAM, PCM, SSD, MRAM, those kind of stuff. Actually, when we say it is byte addressable, like it is truly CPU can access can access the device byte by byte. But the thing is, in our current systems, in most cases, there is CPU cache. So if there is a cache, then probably we need to follow the cache protocol. And there is a thing called cache line. So even DRAM, IRAM, PCM, SD, MRAM, those kind of byte addressable device, CPU can access them byte to byte. But because there is a CPU cache between the compute unit and those kind of memory, so the granularity still need to follow the cache line. And the cache line size is 64 bytes. So if there is a cache if your CPU doesn't have the CPU cache, then the CPU can directly access those kind of devices byte by byte. Okay. And there is some constraint on the SSD part, because SSD, according to their architecture, it should always return the data in a flash patch level. It is about their architecture part, and you will learn it very soon later. So the read granularity for SSD is 4 to 16 kilobytes. Depends on different SSD, like you buy different model, and they will tell you what is the flash patch for that SSD. Okay. So I put several devices together to do some comparison from SRAM, DRAM, hard disk drive, NAND flash, STT, blah, blah, blah. Okay. So first of all is the cell size. So cell size is like for the most fundamental, the most smaller I would say like unit for each kind of I would say more like device than how large it is. So for SRAM, it is like F square is like 120 to 200. So then the unit F here depends on what kind of manufacturing node we are using. If you are using like 2 nanometer, then the F will be 2. So if you are using like 5 or 10 nanometers, then this can be replaced by 5 or 10, depends. So this is just going to let you know, actually SRAM is really super huge, because like one SRAM, there is a like flip-flop those kind of units to gather together to build an SRAM. So it takes a very huge area cost. And DRAM is quite smaller than SRAM. It's just half of the size required. So this is the reason why SRAM cannot offer you so large of the capacity, because you can think about this kind of 120 to 200 F square unit, maybe it can offer you like 1 byte or 1 bit. Okay, so due to the reason, like NAND flash is a storage device, right? And NAND flash price is quite cheaper compared with the memory. If you go to buy a NAND flash now, probably like if you are going to buy a 2 terabyte NAND flash, maybe the price can be very similar to you are going to buy like 16 gigabyte of the DRAM. Okay, so the price for NAND flash is cheap, and the reason is because the area cost, the cell size for NAND flash is super small. So NAND flash now it is around like also like 15 times, 10 to the 15 times smaller than DRAM. Okay, so this is about the cell size. So when it comes to the write endurance, actually it is about if we write the data to this kind of device, actually there is a thing called lifetime. So NAND flash is the most representative one, because the lifetime for NAND flash is super low. Actually, it can only endure like 10 to the 4 to 10 to the 5 of the write. And if you are going to get a larger capacity or NAND flash, for example, if you look at your NAND flash, they're saying, hey, we are using like a TLC or QLC, those kind of stuff. Then actually, the more cheaper NAND flash, which means the endurance usually will become slower. So endurance, it is more like it can only endure the system to write like 10 to the 4 of the amount of data to the NAND flash. Okay, so if the NAND flash now is like 1 terabyte, then it can only endure like 10 to the 4 times 1 terabyte. Like this is the maximum data they can do. Then the NAND flash will comes to a lot of error. So you cannot read out your data correctly. Okay. And the other, just like especially for SRAM and DRAM, there's usually people will not say there is a right endurance because this is like 10 to the 15. So 10 to the 15 actually is super huge. Even DRAM side is like 3 orders smaller than NAND flash, but it doesn't really matter because the endurance now for DRAM is 10 to the 10 more healthier than NAND flash. Okay. And there's two things, read and write latency, and I think this is the most very intuitive, also like metrics that people will care about because it really reflects to how fast the device is. So if you look at the first few, the two column, the memory part, DRAM and SRAM, they're nanoseconds level. Then hard disk drive is so slow, it is millisecond. Okay, and here NAND flash is microseconds. Okay. So millisecond is about 10 to the 6 microsecond. Sorry. Milliseconds is about 10 to the minus 3. Microsecond is 10 to the minus 6 seconds. Okay. And for the write latency, there is a very special stuff as for NAND flash. Because if you look at the rest of the other device like SRAM, DRAM, hard disk drive, or even some emergent non-volatile device, in most cases, their read latency and their write latency, they're very close to each other, right? They're even the same. But NAND flash, it doesn't the case. And we'll talk about this scenario later because when we are going to write the data for NAND flash, and we say because we have a lower endurance, which means our lifetime is not good. So for the writing, we need to always to make sure the data we write into the device is correct. So the write for a NAND flash, you can think about it is about write plus a lot of read, because we need to make sure our data is 100% correct. By after writing the data, we need to read all the data and then to make sure, oh, this is correct, and then we can do another write. So it takes longer time. Okay, so leakage power. So leakage power is like when there is, especially for the volatile memory, like when there is a power on set, and how much of the power we need to make sure the data is correct. What means to make sure the data is correct? Because SRAM and DRAM, they are they are volatile. So even there has very stable power to offer to those kind of device, they still need extra energy to make sure the data is in the correct state. Okay, so for example, because the capacitor for DRAM, actually it is not always in a very stable state, because like the capacitor will drop, right? So to make sure the state is correct, DRAM still needs to always to to reinforce the capacitor to always be in the same stable state. So we need extra power to always to keep the DRAM in the same state as the very beginning when you do the program, when you do the write. So we need extra power, and same as SRAM. Okay, and there are like dynamic power. So dynamic power is about to read and write. So leakage power, you can think more like you don't do any rewrite operation, you just put there, but you still need to make sure the data is correct. And for the non-volatile memory, just like NAND flash or those kind of non-volatile memory, like SDRAM, those kind of, they don't really need that much of power because they are non-volatile. So they do not really need extra power to maintain the data. Okay, but rewrite is another perspective. Like they are called dynamic energy. When we're going to read or write the data, actually, like DRAM, actually you need to take extra time because you need to do a lot of rule-related operation, blah, blah, blah. So actually it takes a lot of time. Okay. So I think in this course we might not have enough time to talk about the right nodes for column, talking about the emergent memory. So I'll first skip the reason why they are looking about the asymmetry energy consumption for this case. But if we have time at the very end of this course, if we talk about this, and we can come back talk about actually the challenge for those kind of emergent memory, what's happened for those kind of device. Okay, so this is the following on will provide you a blueprint about what you will learn from the application level to the hardware level. So first of all, there's an application, right? Or there are a lot of different applications. So applications, when they are going to interact with the storage device, they are going to use system code. Like when after using a system code, actually the operating system kernel can be activated to handle the application's request. So there is virtual file system and then patch cache and then the mapping there. The mapping there, you can think about it, this is the file system because like different operating system, you can have different file system for different disk partition. So inside one like on each operating system, you can see there are a lot of different file systems be activated at the same time. Okay. And then there's block IO there to talk to the hard disk drive, and then there's common device driver, and device driver is about to talk to the device. And usually, like most of the design house in Taiwan now just like MediaTek, Realtek, they spend a lot of time to focus on this kind of device driver stuff. The reason is because their products, they're usually need to talk to the systems, right? So to have a better communication between their products and the systems, they need to have a good bridge. And you can think about device driver is a bridge between those like peripheral products. For example, your mouse, your keyboard, your earphones, those kind of, that are all like end products. So their products needs to talk to the systems. So they need to have this kind of driver to talk to your operating systems, do the management. So there is also device. So on the device there is also software. And the software on the device, we call them firmware. Okay. So firmware here in the Chinese is called 韧体. And device driver here is called 驱动. So this is quite different, but I think in the SSD part, I'll talk more about what firmware will do, and you will have more kind of feeling about what is about the firmware and what is about the driver. So storage device, we'll talk about hard disk drive, SMR, and SSD. And then for I/O stacks, we'll talk about from the device driver, block I/O layer, patch cache, and VFS part. Okay. And then we'll talk about some applications, code design. So we'll talk about the key value store for a database. And then for the graph applications, usually like when we're going to analysis the networking stuff, then we need to deal with the graph. So it is more like the things you learn from your, I think it's discrete mathematics, like Dijkstra or like BFS, those kind of stuff. Okay. And here are two very common storage devices that we are not using in any place, like PC or any 30C device. So hard disk drive, when you open your hard disk drive, you look like this kind of stuff. So there is, in the middle, there is a spindle, and spindle will chain a lot of platers. So your data is actually they're stored on these platers. Okay. To read out the data, actually there is a head. So there is a read-write head here. Okay. And the platers will rotate all the time because the spindle will do the rotate. Okay. And the head can move forward and backward, depends on this kind of actuator. Okay. So this is how hard disk drive works. Oh, one important thing is actually this head will not touch the surface. Okay, because they are using the magnetic force, so the head doesn't need to touch the surface. So if the head touches the surface, usually your head will be destroyed. Like there will be error when you're going to read out. Okay. And the good things for hard disk drive is it is cheaper per gigabyte, and this is reliable. What I mean reliable is the data stored on the hard disk drive usually you can store in a memory like 10 years. This is okay. So this is called reliable. Okay. There is no outer force. You just put there, then you can store your data for a super long time. And this is very important for a storage device because storage device, it is slower. I mean, in the perspective of the asset latency, it is always slow compared with the memory. But the key role for the storage device is to store the data as long as possible, right? You store a movie there, like what you are going to expect is to store for like 4 or maybe 10 years. After 10 years, you plug in your hard disk drive, your data is still there. This is what you expect for a storage device. Okay. But now people are using more about a solid state drive. And the reason is quite obvious because hard disk drive is slow and solid state drive, the latency is between hard disk drive and memory. And then the price for a solid state drive now is actually, I would say very close to a hard disk drive, but because the manufacturing technology getting more advanced and more better. Okay, so this is what you can see. This is very different from a hard disk drive. For hard disk drive, actually, there are all mechanical part. What I mean mechanical part is about the things on the hard disk drive, they will move, right? There are rotations, and then they will move forward and backward. So they are all moving parts. But in the solid state part, actually, there is no moving part. There are all chips. There are cache, there are controller, there are NAND flash, there are all chips. There is no moving part. So this is the reason why solid state drive getting lighter. If you do the comparison, you grab a hard disk drive and you grab a solid state drive together, actually solid drive will be way more like lighter compared with the hard disk drive. And because there's no moving part, so if you like accidentally to drop the solid state drive or hard disk drive on the floor, actually in most cases your solid state drive will be okay to follow the wrong because there's no moving part, so nothing to be break. But hard disk drive, on the other hand, if you mistakenly drop on the floor, in most cases this head will crash on the platers and there will be error. Okay. So faster performance, no wipe. Oh, and there is very important stuff is about the noise, because when you use the hard disk drive, actually you power on your computer, right, and you will hear a lot of noise from the hard disk drive. Especially when you are going to read the data, and this pad will moving forward and backward, and there are all noise. But solid state drive is super quiet. I would say like because there's no moving part. They're using the electricity like principle to read all the data. Okay. So is hard disk drive still necessary if solid state drive now is so cheap, so fast? And what is for the hard disk drive? And I think this answer is quite obvious, just about the lifetime, because the lifetime for a hard disk drive is 10 to the 16, but SSD now, the lifetime is only 10 to the 3. And there is one very obvious challenge for a SSD is if you put SSD here for like more than 3 years or like 5 years and you don't touch the SSD, even you don't touch the SSD, the data stored on SSD, there is very high probability will get damaged, will get lost. Okay, and this is because the architecture and manufacturing stuff on SSD, and you will know why later on when we have a deep dive into the SSD operation part. Okay, so this is just a very simple example to let you know what is 10 to the 3 feels like. Like 1 terabyte QLC SSD can only ingest like 10 to the 3 times 1 terabyte of data writes. Okay, so which means like one petabyte of data, then the SSD cannot be function. Okay, so let's talk about the hard disk drive. So this is the very principle here. You can find it on, I think, most of the place. Then for hard disk drive, actually there is a lot of place, and axle, there is a spindle, and to change those kind of plate. And for each plate, there are two surfaces, the top surface and bottom surface. So your data there can be stored on the top surface and they can be also stored on the bottom surface. Okay. And here is an arm. So on the arm, there is also two heads. Sorry, there are a lot of heads, but for each plate, there are two heads to serve for. So here, this is the read-write head, and here on the other side, there is also a read-write head. So they can work parallelly. Okay, so okay. And the surface of a plater is logically divided into concentric circles called tracks. So this is called tracks. And because this is a concentric circle, so the next track will be a little bit outer and then a little bit outer. So there are a lot of tracks for each plate. Okay. So each track is divided into fixed size of sectors. So each of the piece here is called a sector. A chunk of piece here is called a sector. So each sector usually is 5 kilobyte. And then after 2011, you can also set your sector size to 4 kilobyte. Depends on different hard disk drive manufacturer. So how to rewrite data on hard disk drive? So there are three performance factors will affect the rewrite performance of our hard disk drive. The first is called seek time. Second is called rotational delay, and the third is called transfer time. Okay, so let me give you a brief example on the figure on the right hand side. So this is only one plate, and then there is a spindle. The spindle is outside on the z-axis. Okay, so there are 3 tracks now. Just for example, there are three tracks. And for each track, there is a number, and the number is called a sector number. Okay. So if now the rewrite head points to sector 22, and if the point head is going to move to sector 2, then it will look like this. First of all, it's called the seek time. So for the seek time is the time to move the DX arm to the correct track. So obviously the arm now is in the in this track. So we are going to move to the third track or the outest track, like the sector 2 is on. So this is called seek time. And then because the plate rotates all the time, so we need to, the head needs to wait for the plate rotates to the correct place. Like now we are going to get a sector 2, so we need to wait for it to move for the half of the circle. So there is a thing called RPM, rotations per minute. So rotation per minute is about how fast the moving speed is. So if you go to buy the hard disk drive, you definitely will find a thing called, there is a like 10 to the 1000 RPM or 70,000 RPM now. So using RPM, you can quickly do the calculation. You may know per run for 10,000 RPM will be 6 milliseconds per run. Okay. And there's things called transfer time. So transfer time is about the time to rewrite data to the surface, because we say like this, we need to activate the magnetic force, and the magnetic force will do some things, and then we can read out the data. And then for the next few slides, we'll focus on then how to rewrite the data by using this magnetic force. So I think it's time. So let's call it a day. Thank you, guys.